symplectic Lepage decomposition in positive characteristic. So let me begin. Lepage was a student of Elie Cartan, and so we're talking about symplectic vector space, two-dimensional vector space over some field of symplectic form.
So you will consider finite or infinite fields?
We will consider. Right now, general. In fact, in the beginning, characteristic 0.
Yes.
What this decomposition works in characteristic 0, complex numbers, for example, symplectic form. And we are basically interested in exterior algebra. So exterior algebra of symplectic vector space. There is some k equals 0 to n. So we need some more notation before I proceed further. So I think everybody here knows once, as soon as you have a symplectic form, there is associated bivector, Poisson bivector. For example, if omega is given in canonical coordinates, then this Poisson vector is in dual basis is given like this. So let me make definition.
May I ask you again?
Yes.
What you consider the dual space to Poisson to symplectic space?
Lambda is simply Poisson bivector.
No, but what does it mean?
V is symplectic vector space. This is
algebra.
Exterior algebra of V star. Yes. Differential forms.
All differential forms.
No, not differential, we are a vector space. Only linear algebra in this talk.
Yes.
So, yes.
But linear, you consider only linear forms. Also symmetric forms.
Yes.
In this moment, it's not important that you have symplectic structure at this moment.
Yes, but we are going to now relate.
Yes.
We are going to relate. So, here is the relation. So, we say that a form, K form, is effective if interior multiplication with Poisson bivector, which is k minus 2 form, is 0. So this is okay. So you may recall that I think everybody here knows the interior multiplication operation. Yes, this is form, this is bivector. Result will be k minus 2 form. If it is 0, we say it is effective. Now, what is the idea of this Lepage decomposition? You want to
could you repeat? So you consider lambda k, any k.
Yes. Yes, please ask. This notation is interior multiplication. K form is called effective if omega is called effective when you contract interior multiply by this Poisson bivector, you get 0. This is the definition.
So
Omega is element is a K form.
Yes, K form.
K form. This object will be K minus 2 form.
Yes.
It is 0. We say it is effective. Definition.
Yes.
Okay. So what is the idea? We would like to factorize. So let 0 less than k less than n. Given any k form, we would like to factorize, divide by the symplectic form and its powers in a unique way, unique factorization. can be written as omega 0 plus symplectic form omega 1 plus omega square over 2 factorial. This is even degree, so I write omega power 2, omega power 3, the commute. Raised to omega 2, all the way up to omega power r over r factorial, raised to omega r. So what is r here? R is like, okay, and let me write uniqueness. For uniqueness, we select these forms to be effective. Okay. Omega I, which k minus 2i we start effective. Okay. This is going up to only the middle dimension n, 0 to n. Another statement. To n minus k, similar factorization. Increasing powers. It goes all the way up to omega n minus k plus r over n minus k plus r factorial times omega. Same omega. The same r. There is some. Yes. Okay. This is the before Hodge. Before Hodge did it for the Kähler case, everything. This is very old result. Student of Elikata. He decomposed exterior algebra of symplectic vector space. You want to divide, take any form omega and write it power of symplectic form square of this thing. This is unique. This is theorem of Lepage.
It's some analog of Hodge decomposition.
Yes, but before Hodge.
Yes, before.
Before Hodge. Why they did it? For applying it to PDEs, partial differential equation, Monge-Ampere, and contact geometry, all that. So let me give reference for this thing. Reference is Kushner, Rousseau. I have a book, Contact Geometry, and nonlinear differential equation. Okay, so
what is the reference?
book by for this theorem proof for this theory.
To read this theorem.
Yes, for this proof of this theorem. Proof of this theorem. So by the way, this is characteristic 0. I should write. Of course, because we are dividing by powers omega square over 2, omega cube over 3 factorial, it is not defined in characteristic 0. Also, the proof does not work. Proof is characteristic 0. Best way for this proof, as you know, is if you have seen in Hodge theory, is representation theory of Lie algebra SL2. Maybe I will recall here. There are 3 operations on this exterior algebra: E plus, E minus, H. Standard basis of Lie algebra SL2. Chevrolet basis. What is E plus? E plus is interior multiplication by Poisson bivector. E minus is exterior product with symplectic form. And H is, it takes, so this is, as you know, it decreases the degree by 2 in this exterior algebra. This one increases the degree by 2, and this one preserves the degree. This one, H, wedge K B star to itself, it acts as scalar multiplication. Omega goes to n minus k omega. And they satisfy relations of Lie algebra SL2. So you have representation, as is well known, any representation of SL2 will break into, you decompose into irreducible representations. Yes? And that is this Lepage decomposition. In terms of the, when you have irreducible representation, we talk about highest weight vectors. It is precisely these effective forms. This is kernel of E plus. So these are the highest weight vectors. I do not want to go into this theory because my interest is when this thing fails. I am going to characteristic positive. Okay. So, so the question is, I still have to motivate why I study this problem. Excuse me, I will talk about it a little bit later. But right now, question is, what is happening in positive characteristic? As you know, 2 enters in this Lie algebra relation. So this theory of Lie algebra representation does not work in positive characteristic. Maybe I should also say this theory, SN2 representation theory, is not necessary. You can do this theorem by just brute force linear algebra, symplectic linear algebra. Both proofs are given in this book using SN2 and using just linear algebra. But anyway, for our purposes, it does not work in characteristic 0, cannot even state the theorem. So what can be done? So the situation is like this. For example, when we talk about the relation between exterior algebra and tensor algebra, what is the relation? In characteristic 0, it is possible to view this as subspace, but in general, it is quotient. Yes? Exterior algebra, symmetric algebra are factor spaces of tensor algebra. Same thing here. So let me define. What is this definition?
You can still define it as a...
Yes. So this is definition 1. So I now redefine effective, which works in every characteristic. So let me define. So in terminology of this authors, Kushner, Lisharin, group, so this is algebra. We take ideal in it. Karta ideal is Karta ideal. Simply the principal ideal generated by symplectic form. Everything which is multiple of symplectic form, it forms an ideal in the algebra. Whenever you have ideal, you go to quotient algebra. Def. It means whenever a form is multiple of omega, you set it to 0. Okay. This is called effective forms. So this is definition. So I have sort of 2 definitions of what is effective. Here also there is, so this is, here also I have elements of effective K forms. So I have a problem here now because I have given 2 definitions of this, what is effective K form. Here it is being realized as element of this quotient space. Here it is being called effective is if this definition is there. So I have to make some notational this thing. So this I will call, so all these will be called effective forms. Let me call them. These effective forms I will denote by this epsilon is for effective.
So this is just to fix notation.
Yes.
Epsilon means effective.
Effective.
And
This
the subspace of effective forms, or what?
This subspace I call by tilde. Tilde. Pseudo, some sort of pseudo-effective forms.
Yeah.
For theory of PD, this is necessary. But for my needs, this is necessary. But of course, there is, in the case of characteristic 0, there is isomorphism between this and this, which are.
But can you repeat again what is J?
J is simply two-sided ideal generated by the symplectic form.
So just generated by omega.
Yes, yes. Basically, it means you kill omega.
Yeah.
That's all.
Yes.
So now let me so now I would like to take this theorem and express it in terms of that for generalization. Okay. One.
Lepage theorem.
Yes. Whatever these things tell me about this, I would like to write down. Okay. So.
And can you recall the second statement of your theorem?
Second statement. So the first statement is talking about forms which are between 0 and half the dimension n.
Yeah.
And the second statement is talking about forms which are between n and 2n. So it is saying that so if you begin in 2n minus k form, it is always divisible by at least omega power n minus k over n minus k factorial and higher powers. So I wrote like this form because there is some symmetry. So in this factorization, these are all effective in this sense. Unique factorization. This is okay. So for example, let me show what this means. This is, for example, saying that wedge KV star is equal to effective and ideal. Everything else in the ideal. So direct sum of this fellow is effective K form, and everything else that you're doing is in the ideal. And this is a by uniqueness you get such a statement. So therefore it easily follows that what I was saying, this object.
The second term with or without tilde?
Second term, J is simply J is ideal in wedge. So there is no
here.
Here is
J intersects with
without. Without. It is just the component of J in degree K. That's all. Ideal J in degree K. That's all. So that part of yes, it is only talking about forms which are divisible by symplectic form. And this is the thing. So immediately one can see that this space. What is this space? This is quotient. So it is clear that it's isomorphic to it's isomorphic because if you look at the quotient map, let me put it here. So let's say V star to let's say V star mod J intersect let's say V star this is equal to wedge k epsilon v star. By definition, there is a natural quotient map, and what this thing is saying is that there is a kernel, and I have a complement for the kernel. So therefore, you get an isomorphism between this complement of the kernel and the image. Okay. So in this sense, these two objects are isomorphic. Okay. So let me state, as I said. First statement, in greater than n dimensions, there are no effective forms. It is already clear because in greater than n dimensions, what is happening is that every form is divisible by omega. It is clearly visible here. So
what is n? What is k?
N2n is the dimension of the vector space, symplectic vector space. Here
Here goes
0 to n. So, in other words, yes. In fact, more can be said. Let me say that. It is here that if you are in n plus I form, it is already in the ith power of the ideal. That means it is divisible by k plus 1 power of the symplectic form. Okay, this is power. Whenever you have ideal, we talk about powers of the ideal. So, or in simple language, it is such a form is already divisible by k plus 1 power of the symplectic form. Okay, this is the first statement. The second statement is third statement is that, so okay, we lost this decomposition, but at least this much we can say. So let me erase this piece. Okay, so basically this is called Lepage divisibility, which says that in greater than n dimensions there are no effective forms. The second statement is saying what is the dimension of this space of effective forms in degree k. This is the formula for the dimension. It is just corollaries of this result. No, it's not a new result. And the third part is trying to express the decomposition business in terms of effective forms. It is saying that if you look at k forms which are divisible by omega power L and higher, and mod of the terms which are divisible by L plus 1 and higher, then you are basically talking about omega power L over L factorial times and something here. This is abstract quotient space, but this map is well defined, and this is just what is there. So, what am I? Let me now say what I am going to do. So, this result is going to survive in characteristic P, in positive characteristic, but you have to define this ideal properly. So, I'm going to erase this piece. Any questions thus far? Somebody did not need some clarification. Question. Okay, so here is so if you have the question, I ask the question. So V star or V doesn't matter. Take a 2 form on some vector space. You exist. Does this thing exist in positive characteristic? Let me write like this. If the field has positive characteristic, for example, finite field, question. Is it well defined? Yes, I think so. It is highly, it is unknown, not well known. Maybe it is something easy, but people don't talk about it. Okay, here is the answer is yes. Answer is yes. For example, I give you two answers. First answer is just heuristic. So you take lambda equals Pij, Pi is equal some expansion, and you compute lambda power k. When you start to make the computation, it will automatically be. You will see that the result of the computation is L factorial times something else. So let me repeat. When you take a 2 form, this is special to only 2. Special to only 2. This theory, what I'm trying to say, this thing. When you take a 2 form and you compute its L power in terms of a basis, you always see that it is L factorial times something. So this thing can be, it exists. Let me give simplest case. If lambda is Pij Di by Pj, then lambda square over 2 equals 0. For example, this is famous relation of Klein quadrant. For example, for example in 4 dimensions. So, for example, suppose you are in 4 dimensions, then this thing reads P12, P34 minus P13, P24 plus P14, P21 times E1 plus E2 plus E3 plus E4. It exists. Okay? So, these forms exist. So, let me give the definition. Please note what is the difficulty here. When you say omega square in characteristic 2, it is going to be 0. Omega square is 0 in characteristic 2, but omega square over 2 is 0. Let me put it in quotes. What is omega square over 2? You have to redefine. It exists when you work in basis. So we have to give it a name. So let me do it. You can make this computation. Expand the symplectic form, it will be multiple of 2. It is 0 in characteristic 2, for example.
So just finish it. The L power is always divisible by the corresponding.
Yes, it is divisible, and I want to extract the quotient. So here is, let me give you the, so I call it the PF L lambda is my analog. So PFL is equal to lambda L over L factorial if characteristic F is equal to 0 or characteristic F does not divide this L factorial. but otherwise it is defined like this. Pf0 lambda is 1, definition. Factorial. Pf1 lambda is lambda, and induction, recursive definition, Pfl lambda. If you want to define a form, it suffices to define this for every way. Interior multiplication is equal to okay. This is the definition.
But Poisson vector.
No. This is any not the capital lambda. This is arbitrary. No symplectic business here. No symplectic. Any two form. Any two form. So this is all you have to check is, so in other words, when you apply it to some 2L vectors is equal to applied to V2. This is the definition. All you have to check is if V2 equals V1, then it should be 0. I am saying that this expression defines a 2L form. 2L form. For that I have to check that it is a 2L form. So it is, by this definition,
But
it
what
is
is linear definition?
all V. So in order
V capital denotes space.
vector space, and this is little v for all. Sorry. Okay. So what I am trying to say is, when you want to define a form, if you define its action on interior multiplication with every vector, you have defined the form. So this is the abstract definition, and yes, it can be shown all this is well defined. But if you work in basis, it is simply you try to compute. It is always L factorial times something, and we can extract that thing out. So this is what I call the Pfaffian. Why do I call the Pfaffian? Because in the top dimension, if V is 2n dimensional, then so alpha belongs, so you take some lambda in wedge to V. You take a basis, write it as a skew-symmetric matrix. Then for a skew-symmetric matrix, there is Pfaffian. Yes, we all know there is Pfaffian. So Pf n lambda is equal to E1 wedge E2n times the Pfaffian of the matrix. So once you take a basis, you can there is a dictionary between skew-symmetric forms and elements of wedge to V and skew-symmetric matrices. For skew-symmetric matrices, there is a Pfaffian. It will be that. And these are some generalized quantities in between. So let me not waste more time. And so this definition is there, and I would like to write down some properties. Which part of the work I want to erase? So I'm going to erase.
So that from this point, from this moment, you will speak only on positive characteristic, or you will return to.
No, I will talk about positive characteristic or independent of characteristic. Whatever I am going to say now works in arbitrary characteristic. 0 or positive. But more interesting is positive. Why positive characteristic? Because this work is part of work in error correcting codes, algebraic geometric codes. We take, so I did not yet come, Grassmannian, isotropic Grassmannian over finite field. So symplectic algebra can be done over any field. So we take
But however, can you give any hint? What is your aim, in fact? There are some...
Yes, so here is, so let me talk about it. So, yes, I'm sorry. So let me, but please allow me one thing and I will come back. So some properties here. I will just say what I want to, what is the aim. But I need these relations. Binomial, some binomial identity. So here is the idea. What is this Pfaffian business? So Pf r lambda equals 0. Pf maybe this is the most important property. When you have a two form, when you have some lambda in wedge 2, there is notion of rank, which is special only to two form. Yes, it is the rank of the associated skew-symmetric matrix. Pick any basis. Rank of a two form. So that is characterized by this thing. You start computing first Pfaffian, second Pfaffian. There will be a stage when the arc Pfaffian is non-zero, but the arc plus 1 Pfaffian is 0. R is the rank of this two form. Now let me come. Cartan ideal. Now I return to symplectic vector space. This, what I just said, is general theory of two forms in positive characteristic or arbitrary characteristic. Lambda power L is divisible by L factorial. Is all I wanted to say. No symplectic business here. Now I return to the symplectic business. Ideal generated by omega, but you also want powers of omega, and there it is not automatic. Omega square is 0, so Pf2 omega, Pf3 omega. This is the new Cartan ideal. Okay? Is that clear? So let me introduce similarly Jl is equal to ideal generated by Pf3 omega k greater than equal to L.
Better to denote by tilde, J tilde, because before you denoted by J, it was
yes. So
generated only by omega.
but it is same. It covers. Because like it says here, the Pf2 in positive characteristic I can divide. So this theory includes characteristic 0 as well as any characteristic. Okay. So now I define and the powers of the ideal. Earlier I had power of j square, j cube. That gets replaced by, instead of superscript, I put subscript. Okay, so this thing. So effective forms are this. In positive characteristic, the Cartan ideal I have slightly redefined. Okay, and what is the consequence? So now this thing is my theorem. Krishna.
So it's some kind of refinement.
Yes. So the Lepage decomposition, whatever can be said in terms of the quotient thing, effective forms, instead of the subspace thing. This was, I raised the earlier statement, Lepage theorem. This is the Lepage, the corollaries of Lepage decomposition. If you are not allowed to talk about effective forms as subspace, only as quotient space, these are the three corollaries, these are the three results. All I am saying is that with this new definition, my theorem is that these results are true, and so yes, there are no effective forms, and in higher than n dimensions, the dimension formula and this business. Okay. You may ask for proof. Proof is very simple, only induction on the dimension of the vector space V and linear algebra, symplectic linear algebra. For example, Witt's theorem, linear algebra with symplectic geometry and induction on the dimension of the vector space. Yes, nothing. Yes, linear algebra, symplectic linear algebra, and induction. That's all. That's all. This theorem survives. So now let me come to why I care about this thing. So let me come to the geometry part now. Any questions on this so far? So I would like to add that these things, PFL and these properties, I came upon this in some previous work of mine with my collaborator here, Dinesh Pillai, also in coding theory. All I am trying to say is that these are not well known. People maybe invent it when they need it, but it's a very useful thing, but it is not widely known that in positive characteristic also. Why do I say this? Because I'm going to study Grassmannian, isotropic Grassmannian. Some people who did not know this business wrote a PhD and published some papers in good journals with all wrong results because they did not see that some modifications are necessary.
But I confused absolutely about with characteristic of field. You, at some points you
this
pointed that it's positive characteristic. Now what?
This result is independent of characteristic. The Lepage decomposition, which talks about effective forms as being subspace of, that is using SL2 representation theory, that works only for positive characteristic. And whatever is the resultant positive characteristic, this is still true because this is not talking about subspace. This is not the tilde, this is the quotient. This is true. This is true. We proved it in positive characteristic.
But what is the, I mean, what you want to obtain for as application?
Yes, let me come.
What do you think about?
Yes, let me come to it. So yes, as I mentioned in the abstract, it is about how to realize this symplectic Grassmannian as a projective variety, non-degenerate embedding into projective space. So here, my setup is same. So I am talking about V is 2n-dimensional symplectic space. Symplectic. And I am talking about now Lagrangian Grassmannian, isotropic Grassmannian, k-dimensional, which means k-dimensional subspaces of our vector space V, on which the restriction of the symplectic form is 0. Isotropic subspaces. I will assume everybody knows about this Fluker embedding of the Grassmannian. Grassmannian, if you take some point lambda, I'm overusing this word lambda, you pick some C belonging to GKV, Grassmannian. You pick a basis for it. So this is a k-dimensional subspace. B1, B2, BK basis. Then B1, wedge B2, wedge BK in projectivize it. That is how you embed the Grassmannian as a projective subvariety of this Fluker space. I hope everybody is familiar with this thing. And this is cut out by some famous Fluker relations. Okay. What is the Lagrangian Grassmannian? It is subset of this thing. Subset of Grassmannian. In fact, it is. So my question, since you asked what is the motivation, question is this: there is a projective linear subspace of this Fluker space, which when you intersect with the Grassmannian, the intersection is the Lagrangian Grassmannian. Question is, for our needs, we need embedding into some projective space which is non-degenerate. I will explain what non-degenerate is. Non-degenerate means no hyperplane of this projective space should contain the image. Is that clear? For example, it is famous property of this Fluker embedding. You take some hyperplane, codimension 1 linear subspace. It will not contain the image of the Grassmannian. Why it is necessary? It is necessary for the purposes of where I come from, constructing error correcting codes out of this varieties over finite fields. It is necessary to deal with embeddings in projective space which are non-degenerate. So what is the problem now? The problem, tricky part is, so what is this L subspace? For L is quite easy to say. So which linear subspace in this Fluker space, when you intersect, gives the Lagrangian Grassmannian? Answer is this. If you want, you can put a projective such that interior multiplication with symplectic form must be 0. You take this linear subspace in this projective space, and when you intersect it with Grassmannian, it will mean the intersection of this L with the Grassmannian will be those points on the Grassmannian for which interior multiplication is 0. But interior multiplication for a decomposable object here is simply the same as the symplectic form restricts to 0. This simple linear algebra can be shown. So this is L. Okay. So yes. So in other words, this is yes. So this linear subspace consists of those elements of the exterior algebra you can projectivize such that when you take the all these forms, omega wedge HK minus 2V star, and you take its pairing with C, you should get 0, all such C. Okay? Yes, this is our space L. So what is the problem? The problem is that in characteristic 0, this is non-degenerate, and in positive characteristic, it turns out that this embedding is degenerate. That is the tricky point here, and why. So, I'm almost close to finishing. So here, L as I have defined. But it is also equal to there are two subspaces, L and L hat, and L intersect GKV, L intersect the Grassmannian, also gives me the Lagrangian Grassmannian. L hat is a larger space. When you intersect with the Grassmannian, it also gives you this Lagrangian Grassmannian. So what is L hat? L hat is, yes. So not only, this is saying that all elements in XKV which are annihilated by the Cartan ideal, J intersect XKV star. So this is a bigger space and this is a smaller space L, and therefore if these two spaces are not same, they are same in characteristic 0, but in characteristic positive, these spaces, this is bigger than this space, and that is the trouble. So let me state theorems. Yes, so this is the classical embedding which everybody uses in characteristic 0, and it is non-degenerate only for very small case. Yes, if characteristic of the field is fixed, and only if this k fellow is k over 2 is less than the characteristic, it will be non-degenerate, otherwise it will be degenerate. And this guy is always non-degenerate. These are my results, and so this is only part of the story, because the other part is all what I do with this Lagrangian Grassmannian. That is the interesting part, but that is another subject, algebraic geometric coding theory, which I am not talking about here. Only thing I wanted to say for that is you need to work with non-degenerate embedding. And if you would like to know what is the relation, the dual space of L hat, these are projective spaces, is nothing but the effective spaces. So for example, yes, the dual space of this embedding space is the effective forms. Okay? So, and the proofs of these theorems, again, point is the same. It uses induction on the dimension of the vector space and some symplectic linear algebra, and some clever arguments here and there. That's all. Nothing deep. And of course, the previous results that I developed, decomposition properties of the factoring. So with that, I would like to stop, and if there are any questions, I would like to answer.
Thank you.
So you say this is related somehow to error correction rules?
Yes. So whenever we have inside projective space over finite field, when you have some finite, when you have an algebraic variety, projective algebraic variety, which is non-degenerately embedded, I can cook up a code from it. Yes, I can cook up a error correcting code from it, and yes.
Regardless what type of variety it is?
Yes, it need not be variety. Any collection of points also gives rise to code. No problem. Yes.
So Lagrangian Grassmannian is not anything special.
Yes, it depends what it gives me. So once you read the code, we study how good it is. It will depend. So somebody did it and they gave wrong results. They assume that this embedding is degenerate. So all their work is wrong. Thesis is wrong. Published results in good journal, it is wrong. So I happened to see the paper for review and things like this, so I realized that what is happening is all wrong. So I invented all this Lepage decomposition, everything for the needs of showing that this I wanted to characterize when it is degenerate, when it is non-degenerate. That's all. Okay, thank you.
Thank you.
So I finished in 1 hour.
Let's finish this.